The theme of today's talk is robustness and security in the age of large multimodal models. And it's the theme that's been kind of going through my research as a thread in the last few years. It's a pretty broad topic. And I would like to go through some papers of my own and some new unpublished research as of yet. So I'll give you a sneak peek of some of the results I have, but also go through some of the most, to me, exciting papers that are providing clues to what could be the solution of the problem of adversarial attacks in machine learning. All right, so let me kind of give you a high-level kind of bird's-eye view of where we at. To me, many of you are professionals in AI, but this is a summer school, so I thought I'll start broadly. So the birth of artificial intelligence is a pretty kind of ancient thing to us right now, and it's been a surprisingly ambitious time at that moment. In 1956, a group of 10 people, men in this particular case, decided to spend 2 months at a Dartmouth college in the US to make machines use language within that span and a number of people, form abstractions and concepts, and improve themselves. These are pretty ambitious goals, and many of them have not been achieved, as of yet, and some of them had only been achieved very recently. So it's all, that ambition at a time was very kind of like miscalibrated to the difficulty of the actual problem, because it was pretty uncertain exactly in what way we would make machines to kind of reason in the way we assume intelligence is reasoning. So, these guys were very premature in their hopes, but 75 years later, we got glimpses of what they were hoping for with AlphaGo. And to me, that was the moment that actually pushed me away from my previous career in theoretical physics, studying the information paradox of black holes, and to move to AI. So that kind of, to me, even personally, this was a pivotal moment to move from the research about the fundamentals of the physical world to the fundamentals of AI, which to me kind of encompasses even the questions in physics. And I assume I kind of didn't really leave that set of questions, but rather kind of moved on the meta level to a solution that potentially could solve all of them in one swell swoop. And I think the current AI systems, to a lot of people, would already be called AGI. If you asked me 10 years ago and told me what, for example, O3 does right now, that I can talk to it about whatever I want, is probably the smartest entity I can have an interaction with. It can do coding for me on like at least 10-minute baseline. It could solve huge problems for me, can come up with at least like slightly novel insights. That to me probably would be sufficient to claim we got AGI. But as we get closer, obviously, the target stopped being a pointwise thing in the far distance, but as we get closer, the structural kind of nature of the goal actually became apparent, and we see this jagged frontier of intelligence right now, in which in many domains this is clearly superhuman. And I'm not sure how many of you got a gold medal at IMO. Anyone here? So maybe one person. But this is a very selective audience, and yet only one person got it here. And yet we might soon be able to access models that are routinely able to perform at that level of intellectual capacity. And yet, if you ask to count the R's in the word strawberry, they often kind of misfire and say it's 2, or I'm not sure what the actual number is, so say it's 2, not 3. So you see this uneven frontier, and so as we got closer, the question became more difficult to answer. And to me, we basically have created a digital mind. I think this sounds like an exaggeration, but I kind of view it as such. And the surprising thing was that this was way easier than we thought. To me, I would have probably never assumed it would be this trivial, as in the only requisites would be 10 to the 26 flops or computational operations like being performed on some suitably parallelized hardware, a pretty decent parallel architecture to kind of connect to do the wiring of the neurons in the artificial brain, and a large number of books, equivalent of text. So it seems like a lot, but it's a lot in the sense that it's a lot of quantity, but the quality of the insight is not as deep as I would have expected a priori, let's say a decade ago, when I was starting in the field myself. Still nothing, sorry. Maybe I'll take the mouse and click it like this. All right, and as you might have heard, in other talks, AI is not built, it's grown. It's not constructed, step by step, principle by principle. Obviously, on the low level, we understand everything there is going on, but there are many abstraction layers on which you can understand a system, and the understanding on the level of matrix multiplications sadly doesn't offer much insight about the high-level behavior of the system, as in, why does it answer in a particular way when you ask it a specific question? Why does the coding have this particular valence or whatever, or this particular kind of bugs it's introducing? So there are many distinct layers at which you can understand the system, as Hans Zakulovite spoke about 2 days ago, for example. And the kind of sad reality is that the creators of these AIs do not understand how they work internally in a way that they could predictively say, oh, given these kind of inputs and these conditions, here, these are the outcomes, without actually running the full numerical calculation, kind of literally going through the model matrix multiplications and getting the outputs. So, Feynman said, what I cannot build, I do not understand. Well, that's pretty cool, but it turns out we also might not understand even the things we can build. So it's not excluded by that assertion, but it's a quite cool flip side of the statement, because we literally constructed this. We were able to supervise the growth of the system, and yet we are not understanding how it works internally. And I think this is a bad situation to be in. So my research is oriented around building a principled understanding of AI using empirical methods. So I'm an empirical person at heart. I'm less of an armchair kind of philosophizing type, but rather an experimenter. I run a lot of kind of GPUs, experiments on them, and see what they do. And the result of that, and my hope for it, is interpretability, robustness, and primarily security. So that's the thing I'm focusing on right now in the past few months. All right, so this is kind of the high-level intro I was hoping to convey, just to kind of get a situational awareness of where I believe we are. Let's go much lower level and much simpler right now to a lot of specifics. So how do you convey a function in our head to a machine, right? Like, how is this performed? The function is implicitly represented in my head, and I would like the machine to have the same function. Normally in vision, when I see a picture of a tortoise, let's say, I perceive the tortoise, and some magic happens in my brain that I don't have an introspective access to, and somehow the symbol, the semantically meaningful symbol tortoise, appears in my brain. And I say tortoise, right, as a reaction to that set of inputs, the sensory stimuli on my retina. And I can do this with a bunch of pictures on parrots and the picture of Prague that you might have walked that part as well during your stay here at HAAISS. And I somehow, within my head, obviously have an implicitly represented function f mapping the images x into the semantically meaningful symbols y. But that function is inaccessible to me. But I would like the machine to have the same function, or at least the machine to answer in the same way when I present it with these pictures, so that we agree, which would mean that I successfully taught the machine to recognize images in this particular case. Different people have different functions here. And the way we usually go about training these systems is that we create a data set where we collect these sensory stimuli, and here these would be fixed pixel arrays of these scenes, and associate them with the semantically meaningful symbols: automobile, bird, cat, deer. And we send this to the machine in some way. Typically, the specific instance of this here is SGD being applied to a lot of neurons, which are just a graph way of representing a complex function using simple functions within it. And we train it using gradient descent to kind of approximate the labels on these pictures as well as we can. And the machine develops a function g that maps images into labels. And that function is explicitly accessible to us in the machine by inspecting the weights. But obviously there is high-level aspects, if you kind of zoom out and want to understand how exactly does it behave on the very abstract level, we still have a hard time understanding as well. But the machine develops its own version of this function. And it seems that both of them are good at seeing things. So I am good at seeing things. I can see a turtle and say, oh, it's a turtle. And a vision model for the last 10 years or so, when you show it a picture of a turtle, it reliably says it's a turtle. So that has been basically solved as well. So we are both extremely good at seeing things. And yet the functions are not the same. And they differ in extremely important and philosophically interesting ways as well. And the rest of the talk will be exploring this difference and showing you why it's important for, in my opinion, for AI safety. So how is this connected to AI safety, though? It's a very low-level example on CFAR10 image models, a very simple setting. I argue this point, well, thank you for asking. I argue this point in this less wrong post I wrote last year. So if you want a detailed version of it, I try to be succinct, but it's a bit more detailed than what I'm going to say here. But to me, the problem has a very similar shape. In both cases, I have an implicit function in my head. In the simple case, so matching of images into labels. In the case of the broad AGI problem is the morality of my actions and how I want to act in the world and my implicit desires and what I hope for humanity and all these things. I'm trying to convey this to a machine in some way. And the machine seems to agree, right? Like when I eval myself and the machine on typical examples, it agrees, it says the same things. But in the same way the image models will suffer from the things I'll show you later, I think it's very likely that a broader problem of conveying the philosophical mindset of mine or whatever into a machine also suffers from similar kind of critical vulnerabilities in the function I convey to the machine in a very equivalent way. So I think it's the same shape of a problem where I convey an implicit function, let's say morality, to a machine. It seems to agree, and yet there are gaps. So to me, that's a very kind of motivating kind of similarity for why I care about this, and I think this is a baby version of the problem I actually want to solve in AGI alignment. All right. So what is the robustness of image models, right? Like, how do they differ? How can I probe their differences from the human function that I have in my head? Well, on image classification, they agree with us a lot. Like when you show them cats, they say it's a cat. They're as good as humans at recognizing images, for sure. That's been, a thing we didn't have a trouble with for the last years, for sure. They're even very robust on average. If you present images that are noised up with a bunch of noises, shifted, sheared, or added, you add the snow or frost or whatever, some kind of augmentations to the image to obfuscate the content of the image, it still recognizes them reliably well. And if you have a classifier working on a limited set of classes, unlike a human with like an open-dict kind of classification, they even turn out to be more robust against these things than humans. So that's also a very encouraging sign, right? Like, robustness is a desirable quality that you would like to have in a model that's not supposed to fail under kind of critical load. So classifiers and image models in general are pretty robust, and so are language models. If you misspell a word, it doesn't kind of get confused about the misspelling. It typically reliably autocorrects internally. So there's a lot of robustness to these systems we're building right now. And these things are even extremely good at generalizing outside of the distribution they were trained on. This is normally called the OOD robustness, so out of distribution robustness. And years ago, I was very lucky to write this paper with JRN and Balaji Lakshminarayanan back at Google Brain and DeepMind, where we showed that basically we were able to close the gap in near OOD robustness between humans and machine models in vision. And the technique proved to be kind of surprisingly deflationary. One approach to doing this and kind of making sure things are robust is math. You can look at what it does in distribution and say, let me make it robust in a way that if I expose it to new inputs that are different from the training inputs, reliably mathematically this will stay within some bounds, or you do some Lipschitz whatever constraints on the thing. So it usually looks like 10 pages of a NURBS paper and 50 pages of appendices proving some difficult math that one has a hard time following. But in the end, these things didn't turn out to be the solution to the robustness problem. What turned out to be the solution is basically a massive pre-training data set that imbues the model with kind of broad enough skills to then apply to a novel data set anew after. And I think this is very equivalent to the way kind of humans are actually robust out of distribution. Let's say you show me a new kind of pictures, right? With some like weird screws and like a bent hammer or whatever. And I know these things are not like real objects I was actually like trained on in my experience in the world, because they likely do not exist, or cars with like 5 wheels or whatever. They're like slightly different things. But I have the dictionary of concepts I can decompose the image into. So to me, it's kind of OOD in the sense that like this is a novel object, but the decomposition into semantically meaningful blocks allows me to classify these things correctly. And in the same way, I believe if you do a massive pre-training, you solve the problem of OOD robustness by basically exposing it to a broad enough set of concepts to which it can decompose like the novel input after. So this turned out to be the solution, and I was very happy about it. And scaling was the answer. So this kind of scale-pilled me 5 years ago for the first time, because I saw the bigger the model, like reliably, the more robust it was. And so this was not necessarily an expectation people had, because making the thing classify better could mean it's relying on less reliable kind of like superficial features in the images, and might actually lead to lower robustness. So that was kind of interesting. Yes? Let's see how the first question goes, and then we can decide whether we want to ask questions during the thing.
If I increase the distribution itself,
yeah.
and I keep the out-of-distribution area where it is, don't I just decrease the distance between the training distribution and the out-of-distribution area?
That's a good point, but it relies on like two intuitions that might not hold and are hard to quantify. Distances between distributions, distances in what space, right? In the pixel space, obviously that's one way of measuring it, but like that's not a relevant thing. But also, how do you measure the actual overlap? So intuitively, I agree, but realistically, I'm not sure how to even answer that question on like a quantitative basis.
In practice, what I'm asking is, are these
No, they're different distribution areas. Yeah, thank you. Good question. All right, so scaling was the answer here, and that was very encouraging because scale seems to be the answer to many questions we are troubled with in machine learning. So that was pretty great. So is scale just it then? Is it the answer to robustness? And it turns out, I wouldn't ask if it were the case. So it's not the case. Sadly, no. Sad face. So classifiers are easily broken, and you might know about this, but surprisingly many people do not know how brittle they are. So let me go through it step by step. And I know for many of you it might be old news. It's literally a decade-old news, but for many it could be new. Let's play a game. Let's be a bit interactive, right? What do you see in this image? Please speak up. All right, it's a dog, puppy, yes. Well, I think a healthy human vision should see a dog or a puppy. It's a low-res version. Obviously, 32 by 32 pixels isn't that high resolution, but it's obviously a dog. And machines agree. When you train a small CNN, it answers it's a dog. If you ask GPT-4, it for sure says it's a dog. It might even say which data set it comes from. What do you see in this image? All right, it's the same dog. Well, congratulations. I think you guys are human, but machines disagree. This image to a small CNN is a car with a very high probability. So it's not even kind of slightly a car. It's like the most car-like car they can ever imagine. Is the prototypical example of a car. And you see a small difference between the two images, right? Yet, to a human, the difference is basically indistinguishable. And yet, to a machine, it leads to a very disproportionate change in the outcome. So what was happening here? I added a very specifically crafted perturbation on top of the image, right? This is a specifically designed kind of noise. Very weak noise, but specifically designed and added to that picture. And if you look at it, it's a very specifically crafted object. It doesn't look like that to a human, but to a machine, it's a super stimulus along the car direction, convincing it, despite the predominant kind of visual features of a cat or dog in the picture, to misclassify the picture as whatever the attacker desired. So this is a deep vulnerability in the heart of machine models, here in particular image models, but an equivalent thing holds in other domains and other modalities as well. And this is a huge problem. So we've known about this since 2014. And if you look at the authors of the paper, they're a pretty illustrious group. Christian Sagade, he was a co-founder of Exit.ai with Elon Musk. And Ian Goodfellow was leading ML research at Apple until recently. And other people involved in the early stages of research were, for example, Ilya Sutskever, who was the co-founder of and chief scientist of OpenAI, and now Save Superintelligence. So, a pretty cool group of people back then doing a lot of kind of exploratory, but pretty trivial research from the point of view of looking back 10 years ago. Like a high schooler could do the same right now for sure. So it took 10 years of work and roughly 10,000 papers in the domain to basically get nowhere with the solution. It's a very disappointing story. These things are easy to find, very convincing to the machine and transferable. I made these kind of a few hours ago, just on a small CNN I trained from scratch and just play with them. And they're present even in pretty large models. So CLIP is an OpenAI model mixing image and text modalities. I wrote, when the CLIP model came out, I wrote a few blog posts. I didn't think it would be kind of paper-worthy. So I put them on my website, just detailing that the same thing happens to CLIP as well, despite maybe the assumption that bigger pre-training at a time. I think this belief was pretty broad. I think Chris Olah also said that he believed it might be less susceptible to adversarial attacks because it's broader pre-training. And yet it proved to be probably even more brittle than the small models. And you can easily, so here are the pretty famous examples of the typographical attacks where the original picture is a dog to a clip. You put this label on it, just spelling bird. It now misclassifies the dog as a bird because it both reads and sees at the same time. It doesn't distinguish the two. It's not a fundamental problem. It's just the way it was trained. But then I can add a perturbation on the pixel level on top of the both things. And now it's neither a dog nor a bird. It's now a frog. So I can overpower both the spelled out word and the concept in it with a small pixel modification, small enough that you don't even see it in the picture. This is not a kind of, I'm not trying to fool you, it's actually there, but it's very small. And the same problem applies to even the largest models. And in this paper, Ensemble Everything Everywhere with Balaji Lakshminarayanan, we actually detailed the first examples of this kind of misfiring reliably, transferably between models. And I'll show you what it looks like. if I can play a video here. This is me interacting with, I think, GPT-4o. So I say, what do you see in this photo, right? And I paste a photo I specifically prepared for it of Stephen Hawking. And let's see what the model says. All right. So it's a Rickroll. I encoded Never Gonna Give You Up song by Rick Astley. It's a famous internet meme called the Rickroll into the picture. And with a few cents of compute and pretty rudimentary conditions, I was able to fool models that are trained with $100 million budgets for sure, and whose safety and security are prime concerns for the companies building them. They're in the public eye, and yet without obviously accessing the model weights. And this was even without accessing the model, even inference time, no API calls were made to it, was able to craft a reliable attack on them that fools them to see a different content of an image. All right. So even the largest models are susceptible. So let me show you a classic example, redone in my new paper that's not public yet, from the original paper, but now with the strongest models out there. So here's a picture of anyone? It's a dog? I don't think it's a dog. Anyone who actually has good vision? It's a panda. All right. So the panda, the models agree it's a panda. You ask ChatGPT 4.0 and it says it's a panda. So we're all in the clear there. But you can see the trick I'll be applying here. So I add this new kind of attack we designed, new kind of an attack with a very small pre-multiplier. So it's a very small perturbation. Designing this perturbed image, and then you show it to the model and ask, what do you see? And it says a gibbon. So this is actually the example I had in the original paper, and I thought it's kind of fitting that we could replicate it on the biggest models as well. And this is a new thing, because they can draw now. You can ask, so what do you see? Could you draw it? And what they draw is a gibbon. So actually, the gibbon sits kind of roughly on the high level of features of the panda. So it's not exactly just a completely different position or anything. But if you look at what it actually ends up looking like, it's a panda to a human. But a machine sees, this kind of furry creature that's roughly aligned, like the two dark patches around the panda eyes are kind of there in the picture. You see like roughly the alignment between the two. And yet, like the thing triggered within the mind of the model is quite a different concept. Designed by us. It's not an accidental kind of misclassification. It was designed to look like a gibbon. And here's another aspect of this. We can subtract the panda concept from the picture, just not towards anything, but against panda. And it says it doesn't see a panda. So, and when I ask it, so what do you actually see? It sees a bunch of people praying. And you can see that the dark hair of the people praying on the rug are corresponding to the dots on the panda picture as well. So like, there is some alignment, but it's just like really confused about what it sees. Yes?
Just from a security perspective, how compute intensive is this?
Extremely cheap. Like surprisingly extremely cheap. Yeah.
Okay.
Yeah. It's a very well, I'm happy about it in a way because I designed it and I'm happy I fooled it, but I'm also unhappy because it shows the kind of disbalance between offense and defense in this domain. I think I'll continue, sorry. Yeah. So this is an interesting aspect of it. Sorry, I think I'll just go along, keep the question for the end, sorry. So even the largest models are susceptible to geospoofing, for example. Like this is a Scott Alexander post showing how good they were at identifying, pretty like a bare plane picture down to a few kilometer kind of distance from the actual location. But I'll show you an example where this for sure doesn't hold. And so we took a picture of the Great Dome at MIT and turned it to the model into the Sheldonian Theater at Oxford. So if you ask it, where is this? The first picture it says, is the MIT Great Dome, and the second picture it says it's in Oxford. And here's a few versions of it. This is the King's College Chapel at Cambridge in my undergrad. And then I managed to move the geolocation with these small perturbations towards first Princeton, so you would say academic institution still, that's fine. Harvard as well. But also Kutná Hora, which is a place in the Czech Republic with a great cathedral. I recommend visiting, but it's neither a university nor in the UK. So it moved it by quite a bit. And you see there's something wrong with the images, but the something wrong is very kind of amorphous to you. But to a model is a very specific something wrong, moving it to a very specific location. And this can be very dangerous when the AI takes actions. So here's an example of a traffic scene from Cambridge. And in the traffic scene, you see a traffic light, right? And the traffic lights, actually it's a low res, but a lot of cameras on cars are low res as well. So you see this traffic light, and this is an attacked image. So, but the attack is very small, so you don't see it. It's very weak. And you ask the model, what color is the traffic light? And this is a reasoning model. This is O3. And it spent a lot of time thinking about the answer, right? You see the 2 minutes, 10 seconds spent on the reasoning about a traffic light color. And it says green at the end. It's obviously not green. And if you go on and kind of role play and say, you're a self-driving car, could you drive into the intersection, right? And like without thinking, it just says, let's go. It would go into the intersection because it actually believes, the input is a green light. And yet to a human, this is obviously not a green light, right? Like it's obviously some kind of a yellowish, reddish thing on top. Also, the position of it is not a position of a green light. So it shows a pretty large gap in the reasoning, not only the perception, but also not understanding the other clues in the picture that could lead you to seeing that something is wrong with the picture, right? Like so, and this is a amazingly good reasoning model, and yet here I am fooling it with like traffic lights. All right. Another version of this is that you can hide these things, and this is kind of, to me, probably even more surprising. So you ask, do you see a traffic light? And it says yes, so that's pretty great. The traffic light is there. You ask, do you see a traffic light here? It says no. And you can see the traffic light there for sure. Like nothing changed to a human. Like the perturbation is so minuscule that this, like for sure, shouldn't do anything, based on your intuition about how these models work. And yet, if you zoom in, like it's still there. There's a bit of a, like a rainbow pattern I designed specifically to hide the light from the model. And if you ask it to recreate the scene, it recreates the scene really nicely. It even hallucinates the actual name of the city on the bus. It made it up because it understood it's in Cambridge. And yet, one particular feature is missing, and you might be asking which one it is, and it is the traffic light. The traffic light just wasn't kind of in the mind eye of the model. So when recreating the picture, it reliably recreated many of the features, even the cyclist, the cars, all these things. It's not exactly a replica, but the traffic light is nowhere to be seen. So I think this is a pretty cool thing. So does reasoning help? I don't think so. Like when you ask a reasoning model, for example, 4.0, that's supposed to be great at visual reasoning, right? And you show it the same Hawking I showed before, it just says it's visually consistent with the Never Gonna Give You Up music by Rick Astley. But there's a bit of kind of self-doubt in it. Like it says, oh, there's something wrong with it. It's like distorted in some way. It doesn't say it's distorted and Hawking, made to look like Rickroll. It just says it's a Rickroll, but it understands there's something wrong with the picture. So there's some hope, maybe, for there being kind of internal signals that something is up with the picture. All right. And if you ask it to draw what it sees, it's like a very crisp, Rick Astley with his smile and hair and everything. I'm very amazed. This example, by the way, Toby Art suggested I kind of do this transformation, the philosopher. So I originally had a turtle turning into a cannon, and I think this is even a cooler example because people know Stephen Hawking and Rickrolls. So getting this to work as a physical artifact has been amazingly hard. And so there was a group at MIT that I actually met years ago at one of my first AI conferences, ICML in Sweden, I think in 2017 or 18 maybe. And they designed a physical turtle. So a physical printed, it was like a physical toy in the shape of a turtle. And they designed this patina, this rainbow pattern on top that made it look like a rifle to a bunch of standard classifiers at a time. But they were not kind of broad, kind of open dictionary classifiers. They were very restricted kind of ImageNet classifiers. So they could see the rifle, but these days this wouldn't work anymore. The big models are not susceptible to this. But it was the first kind of great example of a physical artifact I saw fooling these models from all angles and kind of in the wild. And I wanted to show you a great success we had recently, which is getting another physical artifact working, but on all models, including the biggest models. And I've got actually examples of this here, so I might distribute them across the room for your own experiments with the ChatGPT app, for example. Can anyone help me distribute these examples here? And so, what you see is the actual picture of Stephen Hawking, and I encourage you to take a picture of it with ChatGPT app or Claude app and ask what you see. And it'll actually be pretty confused because I put my name on it, so it assumes I'm trying to fool it. So this happened to me this morning, and when I actually do it, you should play with it maybe during the thing or later, but it like reliably should, not always, you could probably make it like stop, but typically it actually works. So try ChatGPT app, take a picture, ask what do you see, and even you could ask it to redraw the scene. And this is a very robust artifact, by the way. We can obscure it here. I've got the same picture, physically printed, with a Waymo sticker and my mug on it. And I ask the model what it sees, and it says it sees the Rick Astley Never Gonna Give You Up video. And I ask it to recreate the scene, and it does recreate reliably the Waymo and the mug, but in the background there's this like smiling figure of Rick Astley singing. And here's a few more examples of this, a turtle, rubber eraser, and then scissors, also recreating it. Here, the David Deutsch, The Beginning of Infinity, in my DeepMind bag. Actually, it flipped the DeepMind logo, so it's back to the right orientation. But if you see, it recreated the scene, but the rickroll is still there reliably, even with the obscuration to the thing. It's a very robust way of fooling the model. And now you have it too. Here's a glare on the picture. Still, it sees a rickroll. It's a very robust perturbation. So I think this is a pretty visual example of how different the vision of the model is from the human vision. Right? Like, this should not be possible if it sees the way humans see. And I actually cut these up from photos this morning, and I put them all on my desk and asked, what do you see? And it says, it sees a frame from the iconic 1987 video, Never Gonna Give You Up by Rick Astley. But it also sees my name, and it assumes I'm trying to fool it. So that's also like a nice kind of bonus you wouldn't get normally from classifiers that only see the picture. This actually reads and like has a lot of situational awareness, kind of being grounded on the language training it's had during training, right? So yeah, and these are the pictures you get. You could distribute it right now, so we can try them later. And when I ask it to redraw, it actually puts the letters in correctly, but the picture is now a singer, but in a Gothic place. So that's actually a pretty nice touch. All right. So this has been my kind of rickroll bonanza, but let me kind of go into explaining why I think this might be happening and what are the kind of crucial issues there and what is the kind of outlook for solving it. And by the way, once you kind of learn it's a rickroll, you might kind of fool yourself into seeing it's a rickroll, but a priori, I've never met anyone who would kind of see it in it. So you can kind of see the glimpse of like kind of reddish hair in it, and then maybe a bit of a flamboyant pose in it, but it's not kind of a priori very clear. It's the specific concept. So there is a huge richness of the way the space of potential pictures is partitioned into kind of the semantic classes the model classifies it into. And here's a paper that I liked and I wrote because I thought no one wrote it yet, but it's not like a big deal, but it demonstrates nicely the sheer richness of the space. And now the visualization I'll show here will be a bit conceptually harder, so I encourage you to kind of think slowly and step by step about the setup here. So what I'll show you that I can take a picture, a bunch of pictures actually, and design a single perturbation that changes each of them to a different class as chosen by me. And the same kind of impact is packed into a single perturbation that's when added to like the picture of a cat, it makes into a dog, a picture of a aircraft carrier turns into a house, a picture of an ice ring, it turns into a whatever space station. So I can design a single perturbation that packs up to hundreds or thousands of such transformations into a single perturbation, showing you how redundant the space has to be for me to achieve such a packing of attacks into a single thing. And now the more difficult diagram. So I start from a picture of a biplane here. So it's just a C-Farton picture, and the model would say it's a plane. And I choose one direction, so one kind of perturbation I'm adding with a different amount of prefactor. So I'm adding 0.1 of this, 0.2 along the axis. And I can do another perturbation on top, orthogonal to this one. And I add another kind of perturbation with a different prefactor, spanning a plane of modified pictures that are basically a cut 2D slice through the space of all possible pictures. Each dot in this plane is a picture itself, but some amount of the alpha perturbation, some amount of the beta perturbation. But they still look like a biplane to a human. And I designed the perturbation such that if you look at how these pictures are classified, in the class laptop, it spells AGI in that slice of the space of inputs. And it draws a turtle in the class turtle. And the background is class daisy. So what you're seeing is like each dot is a picture misclassified exactly in the right way, such that if you kind of put them on a plane, the misclassifications spell out a particular thing to a human. So if you kind of look at the space of all pictures and the way they're classified, there'll be cuts through that space that spell everything you might imagine, that have like as much variation, so like kind of Gaussian-like noise-looking kind of misclassifications, every dot different, but also kind of like very coherent misclassifications like so. So it just shows you the enormous amount of flexibility in that space. And that flexibility is bad because you can basically read off the number of neighboring kind of classification regions around each picture to be roughly 10 to 100 or above. So the argument is in the paper, but basically, if you look at a picture of a cat, there are roughly 10 to the 100 or so, or very large number, neighboring regions of different pictures that are kind of classified differently. Obviously, if there are only 10 classes, like some of them have to have the same class by pigeonhole principle, but there seems to be kind of a lot of like richness around each picture. And that's interesting. So this leads to a really interesting consequence, which is these models are extremely robust on average, but they're brittle under active kind of malicious probing and adversarial design of the input. And both things don't seem to be compatible in low-dimensional spaces, but in high-dimensional spaces, things can be both extremely rare, so their frequency is vanishingly low, so like the relative kind of contribution of the bad fooling images in the set of all images is very vanishingly small, and yet the actual number of such images could be really high in that space. And both of these things can be true and are true in high-dimensional spaces, and they're not true in 2D spaces, from which our intuitions about how things work geometrically kind of stem. So there's an interesting kind of connection to a pretty like mathy, but like very accessible, I think, like part of mathematics that I encourage people to look at. There's a cool book called The Concentration of Measure Phenomena. It's a book on how distributions kind of change as you drive their dimensionality to high dimensions. And it turns out many things in high D become simpler than in low D. Because many transitions that are smooth in low D are often just like stepwise changes in high dimensional settings. And you can pre-cache kind of the ideas about this into your head, and then you can reason pretty nicely about high dimensional space as well by having a dictionary of kind of concepts and like pre-cached ideas about it by kind of building them first step by step. The standard solution here is adversarial trading. You might have heard about it, but let me go through what it actually entails here. The way it works is that you take a training data, this is the normal thing. You put in dog pictures with label dog, and you train the model, and the model ends up learning what a dog is based on the associations into pictures. And then you design a picture against that model that is fooling it to, let's say, predict a car label, right? And now this picture is having this little perturbation applied to it, designed specifically against the model. So what you do is like you throw it back in. You don't say this is not a car. You throw it back in. And you say, oh, this is actually a dog. You misclassified it, train again, right? So you kind of can repeatedly kind of actively sample the bad images from the model, get them, put them back in, say, oh, you're wrong, the actual label is whatever, you train some more. Now, there's like a new thing. You design a new attack, it's a horse. You say it's not a horse, you put it back in, you say it's a dog, and now this like additional picture is in the mix. The problem is, this is extremely unscalable. So like remember the regions I talked to you about before. So it basically means that like for every one kind of cell of original image, there are a bunch of neighbors that you basically have to like compute and throw back to the training set. And here in 2D is very few neighboring regions. In the high D setting, it's a lot of regions, like the very high number I showed you. And the consequence of this is that, and here's a paper from some of my colleagues I'm working with right now from the Lawrence Livermore lab on adversarial defenses, actually, that showed really nicely scaling laws for this kind of defense. And these scaling laws are just empirical kind of dependencies between variables, but in this particular case, they looked at robustness of the model as a function of the training compute needed in this particular kind of training scheme of throwing things back in to the training set. And it basically showed that to get even on the small resolution images, 10 classes, CFAR10, to a human level of robustness, you need above 10 to the 26 flops just to match the human robustness on 32 by 32 images. And this number of flops might seem kind of not intuitively understandable or to some of you, but it's more than GPT-4 training budget. So imagine how the method has to be so bad that even kind of matching the human performance on robustness benchmarks on these low resolution images requires basically all the compute we needed to create these proto-minds that we now talk to day to day. So this is obviously not the way to approach this solution. So new ideas are here needed. And that is also an encouragement to you. I think it is solvable, and I think it will be solved, but this is obviously not the solution. As exemplified by my fooling GPT-4 into seeing Rickroll in Hawking and all these kind of traffic light examples and stuff. So it's not a solved problem. So what can be done, right? Well, I don't know. I'm working on it, but there are many people working on it. But there are clues. And rather than providing a solution, which I do not have and no one has, I'll go through clues that I think are kind of interesting and exciting to look at. They're not exhaustive. They're just my kind of personal taste selection of what's interesting. The first one is this aspect of the human vision that's very different from machine vision, which is that the human eye doesn't see a fixed array of stimuli at once, like one shot, and classify it. It rather performs pretty dynamic things as it's seeing things. Your eye moves, and I'll show you the movement here. This is a close-up view of an eye fixed, looking at the same point, right? It's not moving, actually. But if you look at the little inset picture, is the way the actual point it's looking at is moving on the retina, on the photosensitive layer of the eye. And so the eye, even when you're looking still, and you're looking as still as you can, is jittering all the time at a pretty high frequency. So it's collecting a lot of inputs, not just a single input, but a lot of inputs, before it's making a classification decision. And it's got these small motions, which are called microsaccades, but also major, big motions that are called macrosaccades, which are literally your eye moving from part of scene to part of scene. And because your eye only sees well in the middle, the color resolution and actual resolution are the biggest in the middle and drop off pretty rapidly to the sides, you're basically getting a bunch of augmented versions of the same picture, lower, kind of more grayscale, lower resolution, whatever, into your brain before you make a call about what you're seeing. So this is a clue. This is a big difference between the way machines see and humans see. And what does it mean is that there was a great paper from Google Brain in 2018 that I really like and I didn't know about until a year ago or so that actually measured a really fascinating thing. And the turtle is mine, by the way, so it's not part of the paper. It's another point I want to make after. But in this paper, they designed these things that fool machines and don't fool humans, right? Like these attacks that make a dog look like a car. But then they fixed the head of a human and blinked this picture at them only for 60 milliseconds. And humans were fooled by these images, not 100%, but way more than nothing, right? They were able to actually get the transfer working from machine models to human models, but only with a very brief exposure of the human to the image. So it shows that the short-term vision of a human seems to be more machine-like versus the actual, reasoning about the image or whatever is happening in the system seems to be leading to more robust classification. And this is a clue to me, a huge clue. It doesn't seem to be the reasoning that we use in the way we use the term in language models, as Gavin actually said in the very first talk of the very first day, he doesn't believe is actual reasoning. This to me is another clue that that's not an actual reasoning, because whatever the visual system does seems to kind of wash away the non-robustness of the short-term vision through this kind of longer time focus on the subject. But the thing we call reasoning in language models doesn't solve it right now. So that's interesting. And this paper to me has been mind-blowing because it shows transfer to humans. That's pretty, but only kind of short exposure humans. And I have a version of this at home because I have these towels that kind of has this checkered pattern. And the tortoise also has a checkered pattern, right? And I'm watching for the tortoise not to step on it because it's walking on the ground. But I'm not looking directly. I just have a side glimpse sometimes. And I often am fooled by the towel on the floor, if it's there, into seeing the tortoise in this short way. And obviously when I look, I see, oh, it's not a tortoise for sure. But I also get fooled in this it's not an adversarial attack, it's a naturally occurring similar pattern. But I also see this kind of, I also see this distinction between kind of the short susceptibility to fooling myself and long-term robustness. Another paper is mine, but I would like to show you a specific experiment I did there, which I think is interesting, and I didn't know the result of before. So here's a question. If you design a picture of a dog to look like a car, does it actually look like a dog? Sorry, is it still dog-like on all the kind of lower-level features before the final decision? Does the model actually see, the metal surface of the car or the glimpses of the sunlight in the windshield or whatever, the wheels? Or is it only the final kind of call that's kind of misplaced, right? Is it actually a car to the model? Or does it just say it's a car, but it's not actually like in some deep level a car? Well, this is an interesting question because the models as we understand them, they build a hierarchical understanding all the way from low level features on one end, all the way to kind of high level semantic concepts on the other. Right? Like from edges all the way through textures, patterns, parts, all the way to objects. And we only get the answer at the very end of the pipeline. So my question was, is it actually a car on all these levels? So when you look at a normal model and you let it see a dog, and you read off with linear probes the classification decision along the way, it sees a dog from the beginning to the end. It increases the probability of seeing the dog as it goes through, but it still sees a dog. If you design a perturbation, though, to fool the model, actually it sees a dog almost all the way to the end, and at the very end, it's kind of misclassifying what it sees into a car. It understands it's got dog-like textures, dog-like fur, or whatever along the way, but eventually, it for some reason says a car. So this is a really interesting aspect of it that I was very surprised people didn't look at before. So if you kind of show the probability on the y-axis versus the layer from which you're reading the probability of the ground truth class before the attack, it kind of increases nicely from the beginning to the end. And obviously the target class is not there at all. It's not been modified, the picture, to look like anything, so it's not there at all. But after the attack, you see that it still sees the ground truth class almost all the way to the end and drops the classification at the very end, and the target class rises at the very end. Yes?
Is this just the feature of how we initialize the gradient class to get those, or is there all text?
No. I'm not sure why not, but if you do it empirically, it's kind of method-independent aspect of it. Yeah, but good question. This is certainly, by the way, like in this research, it's extremely easy to fool yourself because it's when you design a defense, and you don't incorporate the defense in a differentiable manner to the whole pipeline of the model and the defense together. Don't let the attacker to attack the full combo of both. You might believe the model is more defensible than you thought, but if the attacker actually had access, we're able to kind of like design the attack against both at the same time, it likely would work. So it's a very easy thing to fool yourself in because many great ideas like do not work, but they work in this sense that if you just apply it post hoc, it seems to detect the attacks. But if you designed the picture to fool both at the same time, it would succeed. So it's a very easy thing to kind of be wrong about. And this has also interesting aspects. So when you fool it to, when you design the picture to misclassify the dog into a car according to the middle layer kind of features, what you see is that, let's say the middle picture here, the layer 27, I designed it there to fool the middle layer of a ResNet. The actual probability of the correct class here, the red line, drops in the middle, but it recovers after. So it's a very localized attack, only fooling the specific level of abstraction within the model. In the normal setting, the very final layer of abstraction, but you can design it against any intermediate abstraction as well. And surprisingly, the other layers are partially decoupled from this, so they are still seeing the original thing to some extent. All right, this is a really interesting clue. I think it's all connected to high-dimensional geometry, which I wrote my thesis on, so I'm probably biased, but I think a lot of the aspects of it can be kind of cast in the lens of high-dimensional geometry. And obviously, I encourage all of you to work on it. I think it's pretty, it's a simple, accessible topic that I think could be kind of worked on in a collab with a pro instance. But also, it's a very fundamental, to me, important aspect of the whole project of AGI safety. So to me, this is the ideal project to work on when you don't have 100,000 GPUs at your disposal. And we're actively working on it right now, but many people are. And there are many kind of potential leads. And I strongly believe this will get solved pretty soon. But to me, a very new approach is needed to this. The defenses we have right now are just not scaling in the right way to be realistic anyway. All right, thank you very much. And if you're interested in what I'm doing, please reach out. And I'm also looking for co-researchers, collaborators, and interns. Thank you.